In this video, we're going to look at relative velocity. To start with, we're going to discuss what relative velocity is, and then we'll have a look at some examples. So what is relative velocity? Well, to consider this, we're going to think about an example of a train with some people on it. So if we have a train, there's my train, and let's say the train is travelling in that direction at 15 meters per second. Now on the train we have two people. We have one person sitting down at the back of the train. They're sort of sitting down at the back, so they're not moving on the train, and let's call him Mr. X. And we've got another person who is walking towards the toilet, let's say, Mr. Y, and he is walking at 2 meters per second. There are two more people in this example as well, outside the train watching. There's Mr. Z, who is standing still, so he has no movement whatsoever either, and he's watching the train go by. And there's also a walker, Mr. W, who is walking in the opposite direction to the train at 3 meters per second. Now, relative velocity is all about how fast it looks like somebody's going from somebody else's point of view. So the best way to do this is to think of it in terms of these examples. So if you're X, you're sat there, how fast does Y look like he's walking? Or if you're Z standing still outside the train, how fast does it look like X is going on the train? So let's look at these examples in turn. We have to introduce some notation, and the notation is for relative velocity. And what this is Y relative to X. And what that means is, what does it look like Y is doing from X's point of view? So Y relative to X, well, both of them are on the train. As far as X is concerned, Y is just moving at 2 meters per second forward. So the relative velocity of Y to X is 2 meters per second. We can think of this the other way as well. What does it look like X is doing from the perspective of Y? Well, if Y is moving forward, it looks like X is moving backwards. So X relative to Y is actually minus 2 meters per second because it looks like X is moving backwards. Now let's think about the people outside. What does X look like to Z? So what is X relative to Z? What does it look like X is doing from Z's point of view? Well, clearly X is on the train that's moving at 15 meters per second. So for Z, it looks like X is moving at 15 meters per second. Notice that even though X is not actually moving himself, he is moving within the train, and to Z it looks like he's moving at 15 meters per second. Similarly, what does Z look like to X? Again, although Z isn't moving, because the train is moving 15 meters per second to the right, it looks like Z is moving 15 meters per second in the opposite direction, so minus 15 meters per second. Now what about Y? This is where we start to get a bit more complicated. What does Y look like to Z? What is Y's relative velocity to Z? Y relative to Z. So Z is looking at Y, and what does it look like Y is doing? Well, Y is moving the 15 meters per second on the train, but he's also moving 2 meters per second of his own accord, walking. So as far as Z can tell, Y is moving at 17 meters per second, the 15 of the train, and the extra 2 that Y is walking. What does Z look like relative to Y? So Y is looking out the window and he sees Z. What does it look like Z is doing? Well, it looks like Z is moving in the opposite direction at the same velocity, because these are negative vectors. Now let's think about W. What does x look like to W? So what is x's velocity relative to W? Well, x is moving forward at 15 meters per second. We've seen that already. But W is moving backwards at 3 meters per second. So in total, it looks like x is moving forwards at 18 meters per second from W's point of view. And again, we can think of it the other way around. What does W look like to x? Well, x is moving 15 meters per second, but W is moving 3 in the other way. So W looks like he's moving the 3 he actually is, plus the 15, because x is moving away from him. So he looks like he's moving at minus 18 meters per second. The final one we're going to look at is y with respect to W. So y relative to W. What does y look like he's doing relative to W? So W is looking at y. He's moving with the 15 meters per second of the train, the 2 meters per second that he's actually moving. But because W is moving the other direction in 3 meters per second, it actually looks like y is moving at all of those added together, so 20 meters per second. And similarly, going the other way around, as with all of these, what does W look like to y? Well, he looks like he's going in the opposite direction, but with the same velocity. So, why is this happening, and can we deduce a formula? Well, yes, we can deduce a formula. And let's have a look at that let's look at x relative to W, make it slightly simpler, as an example to see where the formula comes from. If we imagine that we've got that as our starting point, we have two vectors going on. We have x travelling that way at 15 meters per second, and we have W travelling that way at 3 meters per second. So if we want to know what x is doing relative to W, what does x look like he's doing? Well, if we start at where W is, what does x look like he's doing? X looks like he's doing this whole vector, this way. That is, he looks like he's doing minus W and then x. And that gets us our general rule. Our general rule here is B relative to A, that vector, is equal to the vector B minus the vector A. And this rule is going to help us work with all the types of questions on relative velocity. So now we have an idea of what relative velocity is. Let's move on to have a look at some examples. So, in this first example, we're told that rain is falling vertically at 5 kilometers per hour. So let's draw that in first. Rain is falling vertically, so the vector, vertically down, and that is at 5 kilometers per hour, and that's the rain, so let's call it R. A man is sitting on a train which is travelling along a horizontal track at 40 kilometers per hour. So it's travelling into the rain. So the man is on a train travelling into the rain at 40 kilometers per hour. And that is, let's call T for train, shall we? Call that T. In what direction do the raindrops appear to cross the window? So appear means we're talking about relative velocity. And in this case, it's how does the rain appear to the man on the train. So it's RVT that we're interested in. Now remember, RVT, by our formula, is R minus T. So the vector, we can now add it on using our formula. It's this vector here, going along R and then negative T. So that vector there is R relative to T. Now we've found that, we can see that we're dealing with a right-angled triangle in this case, and we're interested to know what direction the raindrops appear to cross the window, so we want the angle, let's call the angle in here theta. So to find theta, we're going to use a little bit of SOHCAHTOA. So theta is equal to tan inverse of opposite over adjacent, so 5 over 40. Make sure we're in degrees, and we get 7.1 degrees. So the rain is falling at looks like it's falling at 7.1 degrees above the horizontal. We're not asked for it in this case, but we could also find how fast it looks like the rain is falling. That is the magnitude of the vector, so the magnitude of RVT. And this is a right angle triangle, so we can just use Pythagoras' theorem. So it's 5 squared plus 40 squared, all square rooted. That gives us 5 root 65, which is 40.3 kilometers per hour. So the rain looks like it's falling at 40.3 kilometers per hour at a direction of 7.1 degrees above the horizontal. So it looks like it's coming into your face on the train quite quickly. But actually, a lot of that is coming from the train's movement, not from the rain's actual movement. So it's what the rain looks like it's doing, not what the rain actually is doing. Now let's move on to the second example. And this example is all about a plane flying directly west from London to New York. So let's draw that on. We've got a plane, it's flying due west from London to New York, and that's a distance of 5,600 kilometers, and the speed of the plane is 950 kilometers per hour. We're told the wind speed is coming at 120 kilometers per hour from a bearing of 200. So if it's coming from 200, we can draw in our north line, that's north. 200 would be, that's 180 to the down to south, so another 20 degrees that way. So the wind's going to be coming in this direction here, and it is at 120 kilometers per hour. We'll call this one wind, W for wind, and P for plane. Now we're interested in the velocity of the wind relative to the plane, so that is wind relative to plane. By our formula, that's W minus P. So that means we're interested in this vector here, and it's W minus P, so it's in that direction. So that is W relative to P. Now we know one angle in here, but we know this whole green bit we drew before is 200, but we know that this bit here is 90, which means inside the triangle we have 110 degrees. Now we have two sides and the angle between them, so we can use the cosine rule to find the magnitude of the velocity. In this case we're asked for the velocity, so we need to find the magnitude and the direction. So let's find the magnitude first. The magnitude of W relative to P is equal to, or the cosine rule tells us, it's the two sides around it squared, so 120 squared plus 950 squared minus 2 times each of those again, times by cos of the angle. I'm going to run out of space there, so I'm just going to write it underneath. So it's cos of the angle, which is 110. And when we calculate that, we get an answer of 997.4 kilometers per hour. So the wind appears to be going at 997.4 kilometers per hour. Now notice again, the wind is actually only going at 120 kilometers per hour. But because it's sort of coming into the face of the plane, it appears to be going faster because you've got the plane's movement as well. Now we need to find the direction that the wind appears to be coming from, and to do that we're going to find some angles. So we're going to find this angle here, we're going to call theta. So we can work this out using the sine rule, and that tells us that sine theta is equal to 950 times by sine of 110, which is the other angle we know, over what's opposite that angle of 110, which is this, what we just worked out, the 997.4. That gives us, when we work that out, and we do sine inverse to find the angle, that gives us theta is 63.508, but 0.5 will do for now, degrees. So theta is 63.5. But that's not the direction. Remember, when we're dealing with directions, we're dealing with bearings in this case, so we need to find the bearing the wind appears to be coming from. And that measurement, if this is north, that's this measurement, that bearing there. So we know that that bit's 180, so we need to find the bit that's left over in here, this bit here, so we can add it to 180. But if we imagine here, we go up and down, and then up this north line here, we get an alternate angle. So that is equal to this whole angle here. Fortunately, we know this bit is 20 degrees from a similar method splitting up this angle up here. So we have 20 there. So that tells us the bearing that the wind is coming from is equal to, well, it was the 180 plus the 20 plus the theta we just worked out. And if we work all of that out, we get 263.5 degrees. So the bearing that the wind appears to be coming from is 263.5, and it appears to be coming at 997.4 kilometers per hour. Now let's have a look at the third and final example. Now this one is backwards. We're told what the wind appears to be doing. So to a man travelling in a car on a bearing of 60 degrees at 40 kilometers per hour. So let's draw in what we know. The man is travelling at 40 kilometers per hour in his car at a bearing of 60 degrees. Now if it's 60 degrees bearing, that means we get 30 degrees to the 90 to the east. So I'm going to add in that angle there. And he is travelling at 40 kilometers per hour, and he's in the car, so let's call that C. And we're told the wind appears to be blowing from the east at 10 kilometers per hour. Find the true velocity of the wind. So we know that the wind relative to the car is equal to what the information we've got there, but also from our formula, it's W minus C. So this is going to help us sort of work out where the vectors go. It can be quite tricky to spot in these cases, but if we've got wind relative to car, then we have to do minus C. So we have to go along the opposite direction to there. So we have to start at the end of C. And we know if we're starting there, we've got to go east at 10 kilometers per hour. So we're going to get this one here, which is WBC, is 10 kilometers per hour. And that means that in here we have the true wind speed, true velocity of the wind. And if we now look at that now, we can see that we do indeed get WBC, W relative to C is indeed equal to W minus C, which is what we wanted. So that's great. Now we've got two lengths we could do with an angle in there. Fortunately, from where I put the 30, we can work out this one because we've got alternate angles. So this one in here is 30 degrees. Now we can do pretty much the same thing. We can work out W. Rather than working out the relative, we're working out the true velocity. But the same method applies. To find the magnitude of W, we use the cosine rule. The cosine rule is square the two numbers either side of the angle and add them together. and then subtract 2 times each of them, times by cos of the angle, times by cos of 30 in this case, and when we do that, we get 31.7 kilometers per hour. So the wind is actually travelling at 31.7 kilometers per hour. So in this case, the wind is going faster than it appears to be. It appears to be going a bit slower. And the reason for that is actually this time, the wind and the car are going in sort of the same direction. So it's not sort of going against the car, so it would feel faster. It's going with the car, so it feels slower at 10 kilometers per hour, even though it's actually 31.7 kilometers per hour. Now we need to find the angle that the wind is travelling at, the bearing that the wind is coming from. So the bearing that the wind is coming from is this angle here, that's the bearing, if this is north. And we're going to work out this angle here, and then we'll be able to work out the other angle in the triangle and combine it to find the bearing. So theta, in this case, we use the sine rule again, so sine theta is equal to, we take the one opposite is what we normally divide that by, so 10 times by the other angle we know, sine 30, over, and 30 is opposite W. So let's take W, which is 31.7, we just worked that out. We calculate that and then take sine inverse. We get theta is 9.064, and it carries on going. So now we can work out where the wind is coming from. We can work out that extra bit in there. And we work out the bit inside the triangle here is 180 minus 30 minus theta. So that angle there, let's call that alpha. So alpha is equal to 180 minus 30 minus theta, which is equal to 140.94. And then we have to add 90 onto that to get the bearing. So the wind is coming from a bearing of, add 90 onto that, we get 230.9 degrees. So that's what relative velocity is. It's defined by this formula here. B relative to A is equal to the B vector minus the A vector. That's a very useful formula for working with this. But remember what it actually is. It's how something appears to be moving related to something else.